Welcome to Spring LIB.
Okay, which of the following is a correct equatorial hydroxide? This is our first option. And I'm going to go ahead and draw in the other substituent on that carbon to show that this is axial. This is equatorial. So that is not an equatorial OH. There's one substituent. And I'll draw the opposite substituent on that same carbon. And now, similarly, how to the last one, this is axial and this is equatorial. The axial ones are straight up and down, right? So this is an equatorial OH. So I guess the answer here is number 2. We could step through the other ones quickly, though. Number 3 shows an overhead view of cyclohexane, right? Well, recall that an overhead view doesn't correspond to, it can't tell you axial or equatorial. It just tells you whether this OH is above or below the ring. But if you were to draw the chair form, that would just be one form. For example, we could draw this. This might correspond to the overhead view, but it could just as easily correspond to the ring flip conformer in which the OH is here, right? So you can't specify equatorial or axial on an overhead cyclohexane. So for that same reason, 4 is also incorrect. Now the final example is this. And I would point out that 1, this is straight up and down, so it's not going to be equatorial, but 2, there is no position on this carbon that points straight up. The proper positioning of substituents on a chair in this form are straight down for axial and then out and to the right for equatorial. And if you've not been shown this before, you'll notice that basically the way you know how to draw equatorial positions is that they are parallel lines to lines that make up the ring itself, right? So those 3 lines are parallel. If I want to talk about, so is that one. Those 4 lines should be parallel. The other equatorial positions that correspond to parallel lines are these, this one, and this one correspond to these 2 in the ring. And the final 2 are this and this, which are equatorial positions in those center carbons, which correspond to those 2 lines, right? And then everything else is axial, so it's straight up or straight down. Okay, which of the following is correct wedge and dash for this Newman projection? Got a methyl up. Me means methyl, by the way. Bromine down and to the right and a hydrogen in the back. That's for the front carbon, and in the back we've got a hydrogen up and to the left, a bromine up and to the right, and a methyl down. Okay, so we're looking for a wedge and dash structure in which the methyls are anti to each other. That is, it could be such that the methyls are like this. It could be that the methyls are like this. So long as they're on opposite sides of the bond, either through one being a wedge and one being a dash, or just their spatial orientation in the plane. So in that regard, 1 looks incorrect, right? Because we've got a methyl like this and a methyl like this, when in fact we would need this to be a dash for those to be anti. So that's not it. 2 is looking a little better though, right? Now we've got the methyl up and to the right and the methyl down to the left. These are anti to each other. So let's check our other substituents. We need the bromine to be syn across that single bond, right? So if one of the bromine is a wedge, then the other bromine should also be a wedge. Sorry. This is what we're looking for. Wedge and wedge, or dash and dash. If we look at example 2, we actually have dash and wedge. So that's not going to work. If we look at example 3, we run into the problem with the methyls again, where they are no longer anti to each other. But 4 is looking good again. We've got the methyls anti to each other right out the gate. That's good. And we've got the bromines both with wedges. They're syn to each other. Now, it's not pictured, but that implies that the hydrogens both have dashes, which means they're syn to each other. And if we check our Newman projection, we see that the hydrogens are indeed syn to each other. So 4 is the correct answer here.